Today, we're diving into a definitive technical masterclass for professional mechanics. We're going to break down exactly how to diagnose, fully understand, and precisely repair those catastrophic timing chain failures that keep rolling into your shop. Let's get right into it.
Here is our diagnostic workflow for today. We'll start with the anatomy of chain failure, look at the impact physics and damage, run through diagnostic testing and codes, outline the teardown and valve repair process, and finish up with the prevention and maintenance protocol. All right, Section 1, Anatomy of Chain Failure, Engineering the Baseline. First up, let's contrast the two main chain architectures and their specific metallurgical wear patterns. You've got your standard roller chain with a typical 8mm pitch. Here, the wear is intensely localized right at the pin bushing interface. Then you've got the silent chain, or the inverted tooth design. This one is built for higher displacement engines to handle higher loads and reduce noise, and it wears primarily along the tooth flank contact edges. Knowing these differences right off the bat tells us exactly what kind of debris and metal fatigue we need to be looking for during an inspection. Now, here's a crucial point. A timing chain doesn't actually stretch like a rubber band. Instead, the links elongate as those case-hardened alloy steel pins physically wear into the bushings over literally millions of cycles. We call this chain pitch elongation. And get this, the maximum allowable stretch before mandatory replacement is a tiny 0.5 to 1%. To put that into perspective, on a 600mm chain, just 6mm of elongation pushes the hydraulic tensioner to its absolute limit.
So what causes this wear? Well, thermal cycles and oil sludge progressively degrade the nylon guides and hydraulic tensioners until they just can't hold the chain taut anymore. Those nylon guides, they suffer severe thermal degradation once temps creep above 120 degrees Celsius. Add in some abrasive oil sludge, and suddenly you've got a loose chain slapping against brittle guides. But the real killer is the hydraulic tensioner oil pressure drop. It completely loses functionality below 10 to 15 psi. Combine an excessive tensioner piston leakback rate with the inevitable hydraulic lag during a cold start, and your chain is completely unguarded. It's primed for immediate slippage during those first few critical seconds before the oil pressure builds. Moving on to Section 2, Impact Physics and Damage, the catastrophic event. 7.2 joules. That number right there represents the kinetic energy of a 400-gram aluminum piston traveling at 6 meters per second, at 6,000 RPM, slamming into a steel valve exactly when the piston-to-valve clearance is fully consumed. And keep in mind, at 6,000 RPM, this violent collision is happening 50 times per second per cylinder. The metallurgical mismatch here is just staggering. That aluminium A390 piston creates a highly concentrated stress that instantly exceeds the 14.6 Newton-meter yield moment of a 6mm stainless steel valve stem. It permanently bends on the very first microsecond of contact. The result? Instant destruction of cylinder compression. And the worst-case scenario? The piston actually cracks right across the valve relief pocket, turning a standard top-end valve job into a complete, incredibly expensive bottom-end engine replacement. Okay, Section 3, Diagnostic Testing and Codes. Precision troubleshooting. This brings us to the ultimate diagnostic question when a severely misfiring car rolls into your bay. Is it an actual jump chain? Or is it just a sludged VVT phaser? Because oil sludge blocking a microscopic 0.8mm VVT phaser passage can perfectly mimic the exact symptoms of a physical jump chain. Both conditions are going to throw the exact same camshaft correlation codes, effectively locking the phaser in either an advanced or retarded position. But before you even think about connecting a skein tool, you've got to use your ears, make a clear auditory distinction. Chain rattle is a higher frequency metallic tinkling echoing right from the timing cover, and it's super prominent at a cold start before the oil pressure stabilizes. Phaser knock, on the other hand, is a lower frequency mechanical clacking that persists even after the engine has completely warmed up. Identifying this difference early on is absolutely critical to your diagnostic workflow. Now let's map these specific OBD2 camshaft correlation codes to our physical diagnostic flow. Codes P0016 through P0019 show deviation on bank 1 and bank 2. They could mean a real chain jump or just a sludged VVT solenoid. But the massive red flag? That's when these codes are paired with the P030X series codes, indicating cylinder misfires. That combination is a huge warning sign of complete compression loss caused by bent valves. Always remember to verify oil pressure before assuming total internal destruction. So if the fault codes and noises point to a physical jump, you need to follow this exact workflow to perform a compression and leak down test. First, verify the engine is at operating temp and pull the spark plugs. Do your standard compression test, looking for that dead 0 to 40 psi range that screams bent valve. Next, bring the suspect cylinder precisely to top dead center. Connect your leak down tester and apply 80 to 100 psi of regulated shop air. Now just listen. If you hear air hissing out of the intake manifold, you've got a bent intake valve. Air whistling out the tailpipe, that's a bent exhaust valve. It's literally that definitive.
All right, Section 4, Teardown and Valve Repair, the Mechanical Protocol. Once valve damage is confirmed, a pre-teardown bore scope inspection is completely mandatory. This is how you decide if you're doing a cylinder head rebuild or replacing the whole bottom end. Drop the camera down the plug hole and inspect the piston crown for direct valve impact dents. Look really closely for radial cracks spreading out from the valve relief pockets, check the cylinder bore for scoring from shattered debris, and observe the valve head to see if it's visibly deformed or seating off-center.
Here is the strict teardown and verification sequence. First, and this is crucial, never keep cranking the engine once a jump is suspected. Apply lockout procedures immediately. Remove the timing cover, manually rotate the engine to top dead center, and verify if the timing marks on the crank and cam sprockets actually align. Once you pull the cylinder head off to measure valve stem runout, you must discard and replace all torque-to-yield head bolts. Reusing TTY bolts is a massive violation of repair specs. They stretch plastically during their initial installation, so reusing them basically guarantees a blown head gasket down the line.
Now, when you're inspecting the damaged components, precision is everything. Valve stem runout absolutely cannot exceed 0.03 millimeters total indicator reading. And if an aluminum cylinder head went through a thermal event or took a heavy impact, you have to measure flatness across 6 planes to ensure it meets exact manufacturer tolerances. Look at these limits, ranging from a razor-thin 0.03 millimeters of warpage on Japanese engines to about 0.15 millimeters on American blocks. You cannot just eyeball this, guys. A precision straight edge and a proper feeler gauge are absolutely mandatory.
Finally, Section 5, Prevention and Maintenance Protocol, Protecting the Rebuild.
Look, rebuilding the cylinder head is really only half the job. A foolproof post-repair oil system flush sequence is non-negotiable for getting rid of the abrasive metal particles that will absolutely destroy the main bearings. You want to drain the oil immediately following the repair, then fill it with a cheap flush oil or thin mineral oil. Never use harsh chemical solvents, they will eat your brand new seals. Run the engine at idle only for 2 to 3 minutes max. Drain it, thoroughly inspect for metallic debris, slap on a new filter, and fill it with the manufacturer's specified oil. Oh, and make sure the customer comes back for another strict oil change at 1,000 kilometers.
So how do we stop this from happening in the first place? These strict proactive maintenance milestones are the only guaranteed way to prevent tension or failure. You cannot let your customers exceed 7,500 kilometer oil change intervals on these highly sensitive engines, and strictly adhere to the 0W20 or 5W20 specified viscosities. Never substitute heavier oil thinking it gives extra protection. You're literally just starving the microscopic VVT passages. Monitor the hot idle oil pressure, proactively replace the full timing kit between 100,000 and 120,000 kilometers, and educate the driver on a 30 to 60 second idle discipline on cold starts. It makes a huge difference. Which brings us to the ultimate question. If the factory engineering margins are so generous, why do we see so many catastrophic engine failures rolling into the shop? We've seen the precise metallurgy, the tight tolerances, the fail-safes, so why are our bays constantly filled with bent valves?
Here's the truth. The timing chain system was engineered for absolute perfection, but it was never designed to survive neglected oil intervals, incorrect viscosity, or ignored warning codes. Which leaves us with this final thought to chew on. Are your clients truly maintaining their vehicles for the long haul, or are they just slowly counting down the milliseconds to a 7.2 joule catastrophic impact? Thanks for joining me on this explainer. Keep your diagnostic skills sharp, and I'll catch you on the next one.